Hello my friend, welcome back to You Can Do TV channel. Steel hull sections rise and align at Duke Shipyard under careful supervision. Cranes lift enormous plates into place, almost defying gravity, while welders secure each seam with intense focus. Ship compartments are assembled one by one, forming the backbone of the vessel. Even the tiniest misalignment could cause delays, so every detail matters. Machinery rooms, cabins, and cargo holds are constructed simultaneously, allowing systems to integrate smoothly. Pipework, electrical conduits, and ventilation ducts are installed as assembly progresses. It's surprisingly satisfying how massive sections fit together like puzzle pieces. Deck plating is added while structural reinforcements maintain hull integrity. Painting and anti-corrosion coating protect the vessel from harsh marine conditions. Interior fitting follows, including navigation areas, crew quarters, and engine spaces. Seeing teams coordinate on different decks without interference is oddly impressive. Testing of installed systems, including hydraulics, fuel, and electrical connections, ensures proper functionality. Life-saving equipment, hatches, and safety rails are positioned according to maritime standards. Some modules look almost impossible to maneuver, yet they are aligned with calm precision. The ship gradually comes together, embodying engineering, skill, and teamwork. By completion, the vessel is fully operational, ready to sail efficiently and safely across international waters. The Peening Propeller team outfits Fassmer Shipyard's 86-meter patrol boats with advanced controllable-pitch propellers, including the hybrid drive system. 5-blade propellers spinning like this feel almost like a spaceship taking off. Each propeller is hydrodynamically optimized, with carefully aligned blades to ensure maximum efficiency and longevity. Engineers connect the control systems and transmissions, checking torque and response at every step. Components are installed for potential future water hydraulic conversion, showing foresight in design. Once fitted, the propulsion units are tested under simulated loads to verify performance. The scale of these propellers makes smaller machinery look like toys. Successful integration guarantees federal police ships will operate reliably for decades. Every detail is double-checked before departure. Steel strands intertwine into colossal twisted cables at Hendrik Vader Group's Rotterdam facility, each coil demanding exact tension and alignment. Seeing a single strand scale like a tree trunk spin into place is wild. Cranes and rollers guide the cables along the production floor, coordinating every move with precision. Specialized winches manage the massive weight, while engineers monitor stress points to prevent deformation. Once complete, the cables are prepared for transport, carefully lifted onto heavy-duty trailers. The scale of these cables makes everyday machinery look tiny. Safety and balance are critical at every stage, ensuring these titanic strands can reach their destinations intact. The Quintrex 7600 HT yellowfin plate boat begins to take form on the Gold Coast, Australia, with its robust hull panels waiting for assembly. Watching these 6mm bottom sheets and 4mm side sheets being handled is like seeing pieces of a steel fortress come together. All panel edges are pre-aligned to ensure seamless welding and structural continuity. Each weld is tested under controlled stress conditions to ensure long-term reliability in offshore operations. Workers position each panel with precision, while the internal, marine core, rib structure reinforces the hull for offshore durability. Over 80 hours of welding are carried out per vessel, ensuring that every joint withstands demanding maritime conditions. It's surprising how much coordination and focus it takes to weld something this large. Plates are clamped securely, and engineers continually verify angles and measurements to prevent misalignments that could affect performance. As the hull grows, it takes the characteristic yellowfin form, balancing strength and hydrodynamic efficiency. The beam of 2.40 meters and reinforced ribs allow the boat to handle rough waters with stability. Weld penetrations are double-checked to maintain structural integrity under high load conditions. Quality inspections follow each significant weld, and adjustments are made where needed. The hull is cross-referenced with design schematics to confirm all dimensions match engineering specifications. The way the plates interlock makes the structure feel like it could withstand an unexpected storm. All systems are inspected, and internal fittings are carefully installed. The alignment of each panel is logged and cross-referenced with design schematics for consistency. The resulting yellowfin combines toughness, speed, and reliability, ready to meet the needs of serious offshore anglers. Seeing how raw steel transforms into a boat built for the open sea is satisfying. Quintrex's approach ensures that each vessel carries the strength of its materials and the experience of its builders, making every 7600HT yellowfin a testament to Australian craftsmanship and durability. The engine is restored to full operational efficiency after the crankshaft is replaced. On the MS Zaandam cruise ship, the crankshaft exchange is carried out with precise coordination. Pad eyes and lifting frames are used to reinforce existing structures, creating a stable foundation for moving the heavy crankshaft. Quick response crates are always ready to be deployed, ensuring that all essential tools and materials are immediately available for the crew. The crew checks each crate for tool completeness before starting the operation. Reference points are observed to show the original position of the engine, guiding the installation of jacking brackets, which are specifically designed for this type of engine. Each jacking bracket is tested for load tolerance before use. Lifting brackets are then attached and configured to safely lower and lift the crankshaft throughout the procedure. All lifting brackets are secured with locking pins to prevent slippage. A system test is conducted using 60-ton jacks and electrical HPUs to confirm that all lifting equipment operates safely and that the engine block can sustain the movements without displacement. The new crankshaft arrives from Montevideo, Uruguay. Shipping the crankshaft requires strict handling protocols due to its weight. Transporting a 7.5-ton crankshaft through a maintenance hatch is a delicate operation that requires precision and teamwork. The crankshaft is carefully maneuvered into the ship and lowered several decks down into the engine room. Deck crews coordinate signals to ensure smooth lowering. Communication between deck and engine room is maintained continuously. Meanwhile, the engine block is jacked up to the required height to allow the old crankshaft to be removed safely. Set-down and sea-fastening procedures are applied to create mechanical stability, ensuring that the engine remains secure during the exchange. Sea-fastening brackets are tightened to prevent any movement during adjustment. The team performs visual checks to verify stability at each stage. Once the old crankshaft is removed, it is set aside to be refurbished. Even heavy components like this can be managed efficiently with the right equipment. A last-minute risk assessment is completed before the installation of the new crankshaft to minimize potential hazards. Crew members confirm alignment marks on both the engine block and crankshaft. The new crankshaft, weighing 7.5 tons, is carefully skidded into place and lifted into the bearings. Skidding rails are greased and checked for smooth movement. The crew applies careful jacking down procedures to minimize any displacement of the engine block during installation. Each bearing is inspected prior to lowering the crankshaft into position. Brackets are installed to secure the final alignment, ensuring that the engine block is positioned accurately within 1 mm of tolerance. Fine adjustment screws allow precise positioning for optimal performance. The final positioning is verified using precision measuring tools. The precision involved in aligning such massive components is impressive, showing the level of expertise required for this operation. Team members confirm all bolts are torqued to specification before operation. The completed installation confirms the engine is ready for full operational loads. The process confirms that the engine block and new crankshaft are mechanically stable and precisely aligned, ready for full operational load once the procedure is complete. Seeing the old crankshaft prepared for refurbishment reminds that even major components can be reused sustainably. After several days of careful work following extensive preparation, the crankshaft exchange on the MS Zondam is successfully completed, with the engine block aligned and all brackets installed. The lifting frames at IFD show how a lock gate can rise under strict hydraulic control. The crew initiates the lift by engaging the hydraulic frames, letting the gate move upward in steady increments. Kinda wild how smooth a structure this heavy can move, though the mechanism holds firm. As the gate reaches its upper stop, alignment checks confirm stability. Didn't expect the lock's balance system to react this quickly during the final hold. A structure extending over tens of meters, the Imeskip vessel rolls toward the water in Weehai under guided handling. The first action involves securing the hull with support frames before it travels down the slipway. Crews adjust cables to control the descent, keeping the ship steady as gravity takes over. That slow drop feels heavier than you expect for a launch this controlled. Once the vessel meets the water, tugs stabilize its position for the float-out checks. That moment, the hull settles, almost feels like the sea welcoming a new worker. Final inspections confirm alignment, ensuring the ship is ready for outfitting and final sign-off. The grounded MV Bonita on the south coast of Mauritius faced a critical salvage operation. The bulk carrier ran aground, spilling bunker fuel along the shoreline. Salvors focused on key steps: removing liquid and solid pollutants, welding hatch covers airtight, pressurizing cargo holds to regain buoyancy, freeing the vessel from basaltic rocks using explosives or swinging, and finally refloating it. Over 100 personnel coordinated from divers to naval architects, ensuring every step was executed with safety in mind. Portable generators powered electric submersible pumps and welding machines. Helicopters transported equipment and removed contaminated oil. Dyneema towel lines and pressurized air systems supported refloating. Over 5 kilometers of welding and 3.5 kilometers of air hoses ensured airtight holds. On July 27th, MV Bonita was successfully freed and refloated. Seeing a ship rise from rocks like that is oddly thrilling. The Becker Mewis duct slides into position beneath the hull of the crude oil tanker Nautilus, promising a new chapter in maritime efficiency. Seeing a 100-ton device maneuvered under a vessel this size is almost like watching a small spaceship dock. Mind-blowing coordination. Engineers ensure that the duct aligns perfectly with the propeller, minimizing turbulence and maximizing energy savings. Subtle adjustments are made to the bracket system to maintain structural integrity under operational loads. Even the tiniest misalignment could reduce the claimed 6% fuel savings, so every millimeter counts. Once the main assembly is secured, hydraulic systems test the attachment points while the hull integration team inspects welds and fasteners. Electrical and monitoring sensors are connected to track the hydrodynamic performance of the duct. The way the duct channels water flow makes it feel almost like the ship has grown an extra muscle, improving propulsion efficiency with each rotation of the propeller. Retrofitting requires coordination between deck crews, engineers, and crane operators, as the device must be lifted, positioned, and bolted precisely without disturbing the existing hull systems. Some of these moves look like a puzzle where gravity is not on your side at all. Even watching a single bracket being tightened, you realize the stakes for efficiency are enormous. The duct's interior is smoothed and coated to reduce friction, ensuring consistent laminar flow across the propeller's wake. Verification checks follow, comparing pre-installation fuel consumption data with projected post-installation performance. Data from the Nautilus shows a solid 6% energy savings. Those numbers really pack a punch for shipping economics. Crew feedback is collected to monitor handling characteristics and maneuverability after installation. Final inspections certify that structural, operational, and safety standards are met before the vessel departs. Seeing raw metal, bolts, and hydrodynamics come together to save fuel is oddly satisfying. The Becker Mewis duct installation on Nautilus exemplifies how targeted hydrodynamic solutions can reduce environmental impact while boosting efficiency. The combination of engineering insight, precise installation, and rigorous testing ensures that this retrofitted device performs reliably over time. If ships could cheer, this one would be applauding every rotation of its propeller. The success of this retrofit encourages adoption across the fleet, signaling a new standard in energy-saving propulsion technology. Who knew that a simple duct could have such a big impact on a 100,000-ton vessel? The Nautilus team's focus proves that details make the difference between ordinary and extraordinary results. Modules for the Montrose BLP topside are assembled thoroughly at Hydrodynamic, forming a complex structure designed to support offshore operations. Cranes lift each cell deck section from Hull 1 to Hull 2 with astonishing control, while welding teams secure connections that will endure harsh North Sea conditions. Pipe racks, electrical trays, and safety systems are integrated progressively, ensuring seamless functionality across all decks. It's striking how such enormous modules are maneuvered in confined indoor spaces without a hitch. Mechanical systems, including pumps, compressors, and ventilation units, are installed simultaneously to streamline later commissioning. Structural reinforcements are checked continuously, with engineers verifying alignment and weight distribution. Some components seem impossible to place, yet the teams position them with remarkable calm. Painting, anti-corrosion treatment, and insulation protect critical sections, while stairways and walkways are added for safe movement. Hydraulic and electrical systems undergo pressure and continuity tests to confirm performance under operational loads. Watching the topside evolve feels like observing a giant puzzle assemble itself, and the coordination of teams across multiple hulls is impressive. Once assembly is complete, the Montrose BLP topside is prepared for the site move. The loadout procedure onto transport barges demands precise timing and teamwork, as the topside sails to Schiedam before heading offshore. Final checks ensure all systems remain intact during transport. Seeing raw steel evolve into a fully operational offshore platform is both exciting and inspiring, highlighting the synergy between engineering, logistics, and sheer manpower. By the end, the platform is ready to support Repsol Sinopec's offshore production safely and efficiently, a testament to planning, expertise, and collaborative execution. Steel plates and modules converge at Newport News Shipbuilding to form the USS Gerald R. Ford, a carrier designed to redefine naval aviation. Heavy hull sections are lifted and aligned with such finesse that it almost seems impossible for human teams to control. Subassemblies for 2 expansive runways are installed, each welded into place with strict attention to durability and performance. Electrical and plumbing networks thread through decks, ensuring that life support, power, and communication systems operate seamlessly. The scale of this vessel makes you wonder how anyone can navigate coordination of such enormous components. Catapults and arresting gear are fitted, tested, and recalibrated to guarantee that up to 220 airstrikes per day can launch safely. Crew accommodations and operational compartments are structured to support over 4,000 sailors and Marines, while the ship's radar-evading design integrates seamlessly into the hull. Some of these modules are so large that placing them is like solving a 3-dimensional puzzle with gravity as the only adversary. Ventilation, safety, and fire suppression systems are incorporated progressively, each verified under simulated operational loads. Painting and corrosion protection are applied thoroughly across the exposed steel surfaces. Seeing raw steel evolve into a floating city of power is both exhilarating and humbling. Final integration checks align propulsion, navigation, and combat systems, ensuring the Gerald R. Ford will operate efficiently once commissioned. Load testing and inspections precede sea trials, confirming readiness for operational deployment. Watching this carrier come together is like witnessing a small city being built on water, mind-boggling. When complete, the Gerald R. Ford will replace USS Enterprise, CVN-65, ushering in a new era of naval power projection. Engineers and crews at Damon, Sheld, and Naval Shipbuilding coordinate to assemble the Pola 101 at ASTIMAR 20 in Salina Cruz, Mexico. Hull modules are delivered and aligned precisely, each section checked for fit before welding begins. Seeing these large pieces slide together almost feels like a puzzle being solved at sea scale. Welding teams secure each joint, then automated systems verify structural integrity and alignment. After the hull is assembled, outfitting teams install essential systems, including navigation, communication, and propulsion. Modules are tested individually before integration into the full vessel. Final inspections confirm performance standards are met, after which the ship is prepared for delivery. Transporting such a complex vessel through the Panama Canal is a logistical feat that surprises many. The Pola 101 exemplifies modular building efficiency combined with naval expertise. Tons of steel and thousands of tons of ship hulls pass through Oman Dry Dock Company's graving docks every year, each vessel treated with methodical care before returning to sea. The yard begins by guiding ships into one of the large docks at the port of Duqm. Once secured, water is pumped out to expose the full hull for inspection and repair. Dock number 1 and dock number 2, each over 400 meters long, give enough space for VLCCs and LNG carriers to be serviced simultaneously. Workers then inspect hull plates, weld seams, and structural elements for corrosion or stress damage. Damaged plates are cut out and replaced, restoring the hull's integrity and ensuring seaworthiness under heavy loads. After structural repair, sandblasting removes old paint and marine growth, followed by fresh anti-corrosion coating to protect from harsh sea conditions. Seeing each hull stripped down to bare metal reminds you how much the sea can wear away, but also how a yard like Duqm can fight it back. Propeller shafts, rudders, and thrusters are overhauled or replaced. Tanks are cleaned, tested, and sealed to prevent leaks. Electrical and navigation systems are checked and updated as needed. Once all work is completed, the dock is reflooded so the ship can float out, balance, integrity, and performance restored. That moment when the dock fills and the ship lifts feels like giving it a new lease on life. From tiny supply vessels to giant tankers, every ship leaves Duqm Shipyard seaworthy and ready for the next voyage. Hard to believe how many global vessels find their way here for repair, but Duqm handles them all. Crew and cranes coordinate seamlessly to position each turbine tower precisely. Each transition piece from Offshore Structures Britain was rigorously inspected before deployment. Turbine towers from CS Wind in Scotland were lifted and secured with coordinated marine cranes. Blades from the MHI Vestas facility on the Isle of Wight arrive wrapped and aligned for immediate assembly. Siemens Gamesa components from Hull integrate into the turbines, electrical and mechanical systems. Substation equipment is installed both onshore and offshore, ensuring smooth energy transfer. It's fascinating how local suppliers contributed to crucial stages of construction. By project completion, the 659 megawatts farm can power nearly 600,000 homes. Who knew wind could move this much steel so elegantly? Every pipe on the Nord Stream vessel is prepared to handle deep-sea pressure with consistent joint strength. The pipe sections arrive secured on the deck, and crews guide them toward the beveling station to prepare clean edges for the joint. That sharp transition between steps almost feels like the vessel is thinking fast. Once the edges are conditioned, the welding crews position the sections so automated systems can create uniform joints. That jump in heat always catches you off guard for a second. After each weld is formed, the line shifts toward testing, and multiple checks verify alignment and structural integrity. Feels like the whole setup is built to avoid wasted motion. When the weld meets all required parameters, the segment advances toward coating protection to shield the joint during deep-sea placement. The coated pipe is then moved toward the firing line, and tensioners control its descent toward the seabed. The pull on those tensioners almost feels like quiet strength holding everything steady. The last action sends the pipe along the stinger, lowering it into the water in one controlled arc, and that steady glide really feels unexpectedly smooth for such heavy work. Seajack's Leviathan uses its self-propelled jack-up capability to anchor massive turbine components at Greater Gabbard Offshore Wind Farm. Offshore survey teams verify seabed conditions before each deployment. Real-time monitoring of leg pressure ensures even low distribution on the seabed. Hydraulic controls adjust each leg independently, compensating for tidal variations and uneven seabed surfaces. Crew members prepare lifting frames for nacelle modules, ensuring all rigging meets offshore load specifications. Tower sections are hoisted sequentially and bolted together to form a rigid base. Laser alignment tools confirm verticality before lifting the next segment. Sensors constantly relay alignment data to the control room for immediate corrections. The nacelle modules, containing the generator and control systems, are lifted into place by the ship's cranes. Deck personnel coordinate signals with operators to maintain precision within millimeters. Shock-absorbing rigging prevents stress on sensitive components during lifting. Electrical cabling is routed through the tower as assembly progresses, linking each module to the offshore substation. Brakes, sensors, and emergency stop systems are tested before rotor installation. Engineers validate that each safety mechanism operates reliably under simulated conditions. Rotor blades, pre-balanced and transported on specialized frames, are lifted individually. Hydraulic spreader bars attach the blades to the hub while monitoring rotation and pitch. Angle sensors ensure that tolerances meet design specifications for optimal performance. Hub rotation tests and final torque verification secure all connections. Backup power is engaged to maintain operational control. Vibration monitoring systems are installed to detect imbalances before commissioning. Each blade attachment is rechecked after installation to ensure long-term stability. Commissioning runs simulate wind conditions, programming the turbine to adjust yaw and blade pitch automatically. Electrical outputs are compared to MWRA grid standards to verify efficiency and net metering. Every fastener, cable, and interface is checked for reliability. Performance monitoring dashboards track real-time rotation, voltage, and power output. Final inspection confirms that all systems respond as intended. Coordinated effort and precise planning minimize offshore risks and enhance safety. Maintenance access points are verified to comply with offshore safety standards. By project completion, the turbine can produce hundreds of megawatts annually, contributing renewable energy and reducing reliance on conventional sources. The assembly showcases the combination of human skill and sophisticated machinery. It's striking how all massive components come together with seamless timing. Sea-Jack's Leviathan illustrates the engineering and operational standards required for safe, efficient offshore wind turbine installation. Charlestown's 364-foot turbine blades challenge engineers with their enormous sweep. The height of the tower alone makes every lift a test of coordination and planning. Each tower segment is inspected for microcracks before assembly to prevent structural failure. Quick mobilization of cranes and lifting rigs sets the stage for the installation. Crane operators rely on real-time communication radios to prevent any misalignment during hoisting. The base tower sections are first aligned and bolted into position, forming a secure foundation for the nacelle. Reference markings ensure each tower segment is plumb, supporting safe assembly of subsequent sections. Hydraulic jacks are used to adjust tower sections minutely for perfect alignment. The nacelle, housing the generator and control systems, arrives in carefully transported modules. Cranes lift the nacelle onto the tower, guided by experienced riggers. Shock absorbers are installed during placement to protect sensitive generator components. One can't help but imagine the wind pushing against this giant as it waits for its first gust. Cabling and electrical connections are installed within the nacelle, linking the generator to the MWRA grid. Backup power systems are engaged during testing to ensure continuous operations in case of outages. Cooling and ventilation ducts are tested to maintain generator efficiency under all weather conditions. Next, the blades, each precisely balanced and carefully wrapped for transport, are brought to the site. Specialized lifting frames attached to each blade for hoisting. One blade at a time is connected to the hub, the alignment monitored continuously. Laser measurement tools confirm blade angles within millimeter tolerances. The hub rotation test makes you realize the fine tolerances required. Off by just a fraction, and efficiency drops. Once all three blades are secured, final torque checks are performed on all bolts. Vibration sensors are calibrated to detect early signs of blade imbalance. Electrical integration continues, with the generator output wired into the MWRA system for net metering to offset electricity costs. Control systems are calibrated to start and stop the turbine automatically under varying wind conditions. The team verifies emergency stop functionality at multiple points along the tower. Power output is simulated under high wind scenarios before full commissioning. It's surprisingly clever how wastewater, methane, and wind combine to power over 50% of Deer Island's energy needs. Final inspections confirm that safety systems, blade pitch control, and yaw motors respond correctly. Performance monitoring dashboards are configured for 24/7 real-time turbine management. Monitoring software logs blade rotation, voltage, and current for immediate performance analysis. By project completion, the turbine is capable of generating over 3 million kilowatt-hours per year, saving approximately $350,000 annually on electricity. The Charlestown wind turbine exemplifies a successful renewable energy installation, blending modern construction techniques with thorough engineering oversight. Prefabricated panels for the offshore Walter jacket arrive at the site, awaiting careful installation by Mammoet. Seeing panels this large being lifted with strand-jacks makes cranes look like toys. Each panel is checked for alignment and structural integrity before being hoisted. The strand-jacks roll the panels slowly, ensuring precise positioning while minimizing stress on the metal. Ground-based assembly allows teams to work safely and efficiently, reducing risks compared to traditional piece-by-piece construction. Engineers monitor every lift, adjusting tension and angle to prevent unwanted sway or collisions. Once in place, panels are bolted and welded to the jacket frame, forming the backbone of the offshore platform. Safety officers verify all connections and confirm the structure meets design tolerances. Communication between ground crews and lift operators is constant to maintain smooth progression. By using this method, construction time is significantly reduced, and the process is safer for all personnel. Mammoet's approach demonstrates that careful planning and innovative lifting solutions can transform traditional offshore construction practices. It's surprising how much control the strand-jacks give over these enormous panels. The Liebherr LR 11,350 crawler crane tackles extreme lifts in the Netherlands, assembling 6 megawatts wind turbines. The crawler holds steady while lifting a 378-ton load to a height of 110 meters. The crane, operated by Welding in the Netherlands, positions the machine housing of a 6 megawatts turbine with careful coordination. Crawler tracks are aligned for maximum stability, and the power boom extends to reach the high installation point. Safety checks ensure each rigging point handles the massive weight. Operators monitor the lift continuously, adjusting boom angles and winches. The LR 11,350's modular ballast system supports precise load distribution. Even small wind gusts are accounted for during positioning. The final placement is secured, completing the lift with full control. The Liebherr LR 1500 crawler crane dominates the construction site, engineered to handle the most demanding heavy lifts. It is prepared for economical transport, with modules carefully sized to remain under the maximum transport weight of 46.7 tons and a maximum width of 3 meters, 9 feet 10 inches. Its modular design allows quick disassembly and reassembly for complex projects. Each module is loaded and secured to transport vehicles, ensuring safe arrival on site. Transport securing brackets are double-checked to prevent shifting during transit. Once on site, the SA frame is positioned, and winch IV, permanently reeved, is prepared for operation. The central ballast is assembled, consisting of only 4 slabs, with the upper slab serving as an access platform for operators. Winch I is set up as the only main hoist, while Winch 2 is installed as an auxiliary hoist. Ballast handling equipment ensures safe and easy placement of all ballast elements. The assembly ballast tray is connected to suspend the ballast sections at variable radii ranging from 9 to 16 meters, 29 feet 6 inches to 52 feet 6 inches. Operators verify that all safety equipment is in place before lifting. The crane's maximum lifting capacity of 500 tons, 550 UST, is achieved by configuring the assembly ballast wagon correctly. The ballast wagon is positioned, and the driving mode is set for parallel operation or towing, depending on the site requirements. Boom combinations are arranged to allow the crane to perform a wide range of lifting applications. Additional guying with aramid rope stabilizes the structure during lifting operations. Suspended ballast weight is continuously monitored to prevent overload conditions. The SA frame is fully integrated with the central ballast, creating a stable base for subsequent lifts. Winch IV is engaged for precise hoisting control, while Winch I handles the main load, and Winch 2 provides supplementary support. Each lift is carefully monitored, with the variable radius adjusted to accommodate the boom length and load weight. Ballast sections are repositioned as needed to maintain balance, and suspended ballast elements are secured to prevent shifting. Sensors alert operators if any section moves beyond acceptable tolerances. Crawler drive provides four-fold traction, enabling smooth and controlled movement of the crane across the construction site. The boom is extended according to the required lift radius, and all winches are coordinated to maintain alignment. Central ballast slabs support the entire assembly, allowing the crane to maintain stability under maximum load. Operators adjust the boom angle and verify the suspended ballast positions before executing lifts. The LR1500's track system reduces ground pressure for safer movement on uneven terrain. During complex lifts, assembly ballast trays and suspended ballast are managed to ensure load balance and safety. Boom combinations are adjusted to match specific load requirements, and additional aramid guying ropes are deployed where necessary. The crane's hydraulic systems are engaged to control winch tension, and operators confirm that both main and auxiliary hoists respond correctly. Real-time telemetry allows continuous monitoring of crane stability. Each lifting operation is performed in stages, with the SA frame and central ballast constantly monitored. The upper access slab allows operators to safely reach the boom and attachment points. Ballast wagon driving modes are selected according to site conditions, and all elements are rechecked before proceeding. Variable radii adjustments are used to optimize the lifting geometry and maintain the crane's balance during each stage. Final checks ensure the crane can perform heavy lifts safely. Maximum lifting capacity is validated through controlled hoisting tests. Boom combinations, central ballast alignment, and suspended ballast stability are confirmed for all configurations. The LR1500 crawler crane's assembly is complete, with all modules, winches, and ballast properly installed and operational. The crane's configuration flexibility allows adaptation to multiple lifting scenarios. The crane is ready for heavy-duty lifting tasks. with full control over boom, winches, and central ballast adjustments, enabling safe, precise, and efficient operations. The LR11350 crawler crane stands ready in Venice, its 950-ton lifting capacity about to be put to the ultimate test. Each structural element of the crane is inspected and tensioned before the lift to ensure stability. The reactor, weighing nearly 950 tons, is carefully positioned on transport skids. Coordinated radio communication keeps all crew members in sync during the delicate operation. Hydraulic jacks and supports maintain precise leveling of the reactor as the crane prepares to lift. Rigging cables are attached and double-checked, each rated for the enormous load. It's impressive how engineering calculations translate into real-world lifting accuracy. The crane's tracks are adjusted to ensure even weight distribution on the quay. Load cells monitor stress continuously, providing real-time feedback for the operators. Once the rigging is secure, the reactor slowly rises. Every millimeter of movement is carefully logged to prevent imbalance. Dock workers signal the crane operator to rotate the load for alignment with the barge. Temporary supports are in place to avoid sway from wind or minor vibrations. Engineers verify the lifting path and clearances, ensuring zero collisions. The reactor clears its original position, gliding over the quay as the crane operator maintains smooth tension. Observers can't help but marvel at the precision and coordination required for this lift. Finally, the reactor is lowered onto the barge, its position secured with C-fastening brackets. Checks confirm alignment within millimeter tolerances. The LR11350 retracts its boom carefully, leaving the reactor safely aboard the transport vessel. This operation demonstrates the combined expertise of operators, engineers, and riggers in moving one of the heaviest single loads in industrial transport history. Venice's quay becomes a stage for heavy lifting mastery, blending physics, skill, and teamwork.